Hello everyone, and welcome back. Today I would like to talk about a type of problem that is not uncommon in a first-time physics course. It is also not uncommon on the AP exam and tends to seem difficult at first glance. However, for the type of problem I'm about to show you, once the connection between linear and angular is made, the problem will simplify pretty quickly. So let's talk about our situation. Here I have a ball. We'll simply call that object A. The ball is moving to the right, which means it has an initial velocity. The ball is going to bounce off this object, I'll talk about in a minute, which means it will have a final velocity. Now this object, which I will call object B, is a metal bar attached to a hinge. The hinge is right here, and this is an above view, so we could ignore any gravitational forces. Now this bar is attached to a hinge at the very end of the bar. The ball moves to the right, hits the bar, and bounces off, which means the bar is going to swing around this way after the hit. Here is the question. A 2 kilogram ball moving to the right at 8 meters a second hits a 7 kilogram metal bar attached to a hinge. The bar is 3 meters long, and the ball hits the bar at a right angle, which is going to be important, 2.7 meters away from the hinge. So right at that statement, I'm going to label this distance, which is going to be a radius, because the ball is going to hit at a right angle at exactly this distance from the center axis of rotation. The ball bounces off the bar with a velocity of 6 meters a second. What is the angular speed of the bar after collision? So I'm going to add some things into my drawing. Velocity to the right is 8 meters a second. The velocity of the bounce is 6 meters per second in the opposite direction. All right, let's start out how we usually start, by listing givens. I'm going to make the ball object A, so mass A is 2 kilograms. Velocity initial is 8 meters per second. Velocity A final, it's going back the other way, so I'm going to make that negative. This will translate to rotational, but I will discuss that in a moment. Mass object B, which is the bar, is 7 kilograms. The length of the bar is 3 meters, and the distance the ball hits the bar is 2.7 meters. And again, that's a distance from the axis, so I'm going to call it a radius. So here's where everyone gets stuck. This ball is hitting the bar. This is obviously a very linear situation here. It bounces off, still linear. However, once we translate to the bar itself, the bar is going to rotate. So how do you make the connection between the linear information of the ball and the angular information of the bar? Well, I'm going to actually pause this problem right now completely and have a discussion on that. All right, for starters, I'm going to put our angular momentum equations at the bottom here, and I'm going to bring back our ball and bar combination, object A, object B, and the ball moves to the right and hits the bar at a 90-degree angle. And here is the axis, which is going to be important. Now, next to this, I'm going to put up a different situation. Here's my ball. I'll just call it object A again. And this time, the ball is moving in a circular path. Well, if the ball is moving in a circular path, counterclockwise around this axis, that means at this location, when it's at the very bottom here, the direction of velocity is tangent to the circular path. If this ball is moving at a velocity tangent to the circular path, that means it's at a 90-degree angle to the radius. And you may have noticed, if this is a singular object moving around a circular path, it's going to have a moment of inertia. And the moment of inertia for a single object moving around a circular path was this. Moment of inertia of a point mass is mr squared. And if it's moving in a circular path, it also has an angular momentum, which is right here in the lower left corner. In fact, I'm going to take that and put that right here. Now, here's the important connection. This ball is moving to the right and hits this bar. At some point, the ball hits the bar right here going this way at a 90-degree angle or near enough to the axis. Here's the radius, here's the velocity. You can say there's a slight angle here, but that is typically so little of a rounding error, it is ignored. And if I look at this situation and this situation, they are identical. At this exact moment in time, I have a radius and a right angle to the velocity. At this exact moment in time, I have a radius and a right angle to the velocity. So here's my connection from the linear to the angular. Now, let's talk about how we make that connection mathematically. Well, if you remember, if you ever want to translate from linear to rotational, you have to use one of these three equations. And you are typically using this middle one right here, which we're doing right now. And the connection I'm going to make is with omega. Omega, I'm going to divide by r, is velocity over r. Now, all I'm going to do is take our moment of inertia equation and our linear to angular translational equation and stick them together in this equation right here. If I do that, I get mr squared, that's the moment of inertia, times v over r. That's in this equation over here. You may notice immediately radius cancels, which means I have mrv. This is the equivalent angular momentum of that ball hitting this bar at a 90-degree angle to the radius with this velocity, which means in this case, I can literally use this equation as angular momentum, either here or in our angular momentum collision equation, which is what we're about to do. A small note on this before we continue, however. In the problem we are doing right now, the velocity is hitting at a perfect 90-degree angle to the radius. However, if you ever see a problem where the ball hits at an angle like this, you will need to get the component of that velocity that is perpendicular to the bar. In other words, the assumption is this does make that 90-degree angle. So if it hits the bar at an angle itself, you would have to split it up because this vertical component would not cause this bar to swing at all. In other words, this velocity vector goes straight through the axis. You don't have a 90-degree angle to the lever arm. Another way to put it is, I can call this V perpendicular, which I think I will. All right, now let's go back and take a look at our original problem. And I'm going to take the equation we just derived and put it up in the corner here so it's out of the way. And let's get to work. Now for starters, this is a collision. Biggest rule for collisions is momentum is conserved. Angular momentum initial equals angular momentum final. There are two objects, so initial A plus initial B equals final A plus final B. At the beginning, the ball is moving, but the bar is not, which means since there's no velocity or angular velocity for the bar, there is no initial angular momentum for the bar either. After the collision, the ball is moving and the bar is moving, so everything else stays. I'm now going to expand this. Here's where a big connection comes into play. The ball is technically not moving in a circular path. However, we just derived that at the moment that it hits the bar, the fact that there is a part of the velocity that is a 90-degree angle to the radius means effectively that it has a rotational momentum. Therefore, the angular momentum of the ball at the hit can be defined as mass A, radius, velocity initial. Remember, the velocity has to be perpendicular to the lever arm, which it is because we said it's a 90-degree angle, equals the ball bounces off, mass A, radius, velocity final, plus the bar is moving rotationally, so I'm just going to keep the rotational equation, moment of inertia of the bar, and final angular velocity of the bar, which is what we are looking for. Now that I set up this equation, let's check off what we have. We have the mass of the ball. We have the radius, which is the distance that the ball hits relative to the axis. We do have both velocities of the ball. Here's the hit, here's the bounce off. The only thing missing then is the moment of inertia of the bar. So like I said before, the ones you're expected to know are the point mass, ring, puck, and sphere. So the moment of inertia of a bar, where the axis is on one end, make sure you keep that in mind because it would be different if the axis was dead center here, is 1/3 ml squared. Again, this is not something you're expected to know. There should be a table or chart, or sometimes it's flat out given to you. All right, I'm going to do a little algebra here. First, I'm going to subtract this from both sides. That will give me this on the left-hand side. I'm going to replace in the moment of inertia equation, and omega final is what I'm looking for. Now, the next step, I'm just going to clean this up and get omega f alone. First, let's multiply everything by 3 to get rid of that denominator. I'm going to factor out the MAR. Now, the MAR, VI minus VF. I'll then divide by ML squared. That is mass B, by the way. And now an equal omega final. I'm going to move things around a little bit so we have some space. So omega final equals 3 times mass A, which is 2 kilograms, times radius, which is 2.7 meters. Now, this part's kind of key. VI is one way, it's 8 meters a second, minus the final velocity is in the opposite direction, negative 6 meters a second. So you have a double negative here. This is effectively impulse. The ball bouncing off something will apply more impulse than if it just stopped. Mass of the bar is 7 kilograms. Length of the bar is 3 meters, and this is squared. Okay, before we continue, I'm going to check units. First off, these kilograms are definitely canceling. I'm going to have meters squared here, so there's 2 of them. Well, 1 cancels with this one here. The meters per second here are going to combine. So these meters are going to cancel with the other one here because of the squared. And that means the only unit left is the 1 over seconds from when you combine these. And again, since we have radius in the mix here and we're going to rotational, this is effectively going to be radians per second. Because again, radians is a fake unit. And anyone who is not sure why I keep saying that, you need to watch my intro to angular video. And if we complete this calculation, we get 3.6 radians per second. And that is the angular velocity of the bar. So if you notice, this problem was pretty much just a collision problem. It was a rotational collision problem. However, the most important part was this connection, the connection between the linear and angular. In short, MRV is the angular momentum of the ball as it hits, as long as the radius and velocity are at a 90-degree angle. Once you know that, you can literally just shove it into the angular collision calculation. Another way to put it is this middle part of the video was the most important part when I actually did that derivation. And a reminder that I keep saying, this must be at 90 degrees for that to work. So if the velocity ever hits anything other than 90 degrees, you will need to get the perpendicular velocity. All right, hopefully this helped you out. Have a good day. This is Mr. M, signing off.